Hi everybody and welcome to the AWS AI UG 7th edition. We're here this evening with two fantastic speakers, Phil and Robert, but before we get on to those, just got a few things to run through. So for those who don't know me, hi, I'm Ethan Sumner. I'm the co-founder and CEO of CommunityStack, and we're on a mission to build the next generation of social infrastructure. So you're probably wondering, what does that mean? Well, essentially we run practitioner communities, conferences and platforms that help technical and the third sector rely on, depend on. So this, for example, can be this meetup. We've got different communities across DevOps, cloud, platform engineering, Azure. We've recently acquired GCP London as well. So we've got a full spectrum there. We're also building numerous different community platforms, which we'll talk about a little bit later on, and doing a lot of work within rural digital inclusion, and also kind of long-term research and innovation, particularly within community groups, but also in wider areas, including special educational needs and solutions for people with disabilities as well. So CommunityStack has essentially got 6 different pillars. So ecosystem, which is all the events which you've just spoken about. So as I said, you're here this evening watching one of our meetups, but we've also got numerous different conferences. We've got one in Leeds next week. We've got 14 tickets left. So if you want, make sure to get one now before they sell out. But we've got some fantastic speakers, including Matthew Skelton and other kind of famous DevOps names, including Andy Bergen, on stage. It's in Leeds, got 120 people. It's awesome. We've then got Engine, which is our next generation of community platform. Essentially, we're trying to build a competitor to Meetup. I've grown quite frustrated of Meetup, and a lot of other organisers are. And we're actually all getting together on Saturday. Quite a few London-based organisers, run by an amazing chap called Hugh, who's quite a famous London community organiser as well. And we're going to be discussing all about, what's next for the Meetup community and stuff like that. And we've also launched Switchboard in the past week. So this is our full-service digital platform for the third sector. So myself and my co-founder, who we'll talk about a little bit in a moment, we basically got together a year ago and went, how do we solve the problem of a lot of charities aren't visible, visibly digitally? A lot of non-technical trustees can't build a website. So we basically came up with the problem statement of, can we allow a non-technical trustee to build a fully accessible presence in under 10 minutes? And we're pleased to say that we've done it, and you can actually do it a lot faster than 10 minutes as well. And it's also completely free. And we've also just got the ability to do custom domains and custom emails. I know a lot of people are quite upset over the recent changes with the 365 removing licenses for a lot of non-profits. So we're able to provide a lot of free and very low cost email solutions and other kind of stuff there. But we're doing a lot of stuff. And we're also doing work within the enterprise as well, building an internal community platform. And then through our labs team, we're researching numerous different areas and different solutions. And we're aiming to do a hackathon later this year around special educational needs and other kind of areas as well. So if you've got an interesting kind of research or pilot idea wanting to run with the community landscape, please get in touch there. But we've got numerous different campaigns which we're working across numerous different policy areas, which you can find on our website. So you probably know who I am if you're watching this on LinkedIn, but I've been organising communities for several years. I've run over 100 of them. 100 different events, which is awesome. I'm building CommunityStack alongside my amazing co-founder, who's a fantastic engineer, and is really key to all the amazing work that CommunityStack does. Called Mercedes Moxon Greenfield. She's a former UK robotics champion and a true accessibility advocate. And we're both from South Yorkshire, building this out of the UK's first tech town in Barnsley. So yeah, there's lots of awesome stuff going on. But there's also a wider team behind the scenes, which you often don't see. We've got Rebecca in legal, we've got Lacey in marketing, we've got Sam Barker, our exceptional designer, and we've got a new developer who's just given him the role today, so he'll be joining soon. And then we've got Jan, who's our other developer intern, and then we've got Adam, who works in policy as well. So we're rapidly expanding as a team with more hires coming along soon. So it just shows, we're doing a lot of good work there. So, but you can find majority of our meetups on Meetup if you scan until we launch Community Engine later this year. So if you scan this QR code here, it'll take you to our Meetup page. And we regularly run probably about 4 or 5 a month at the moment, sometimes more. So we've got numerous different conferences as well. But we'd like to thank our amazing sponsor for today, Overmind. It's run by an incredible chap called Dylan Radcliffe, who's based out of San Francisco, but originally in London, very kind of popular in the UK community scene. But he's ex-Puppet and Perforce, and he's built this exceptional tool called Overmind, which is around Terraform and incident management. I'd highly recommend you check them out. It's an awesome tool, and it's kind of like maps everything out. It's fantastic. I'm probably not doing the best job selling it, but if you scan the QR code, it will take you to their website. You can find it much more. So we just want to say thank you very much for joining. We're going to go on to our first speaker, Phil, this evening. If you've got any questions, please feel free to put them in the chat or on YouTube or on LinkedIn, and then I'll bring them on towards the end of the session. But that's enough of me, and on to our first speaker of today, Phil. Cool.
Hi, everybody. So my name is Phil. So just share a little bit about me when I'm bringing up the talk. I work for Cognizant in the UK, and I'll be talking about how we use AI within a number of use cases, and explore the kind of practical bits of it. But just to give you background, I live in Ipswich in Suffolk in the UK. I do various things. I have a golden jacket, so I have 12 AWS certs at the last count. I also have two young children, so I have two children, one age 12, one age 8, so they keep me quite busy. And I also do a lot of work for charities in the Ipswich area as well. So me and a bunch of people, mates, have raised kind of nearly 50,000 in the last 5 years for local good causes, things like supporting cancer patients when they need care and other things kind of in that area. So if you want to check that out, it's called Calm Crew on Facebook, and it's all about a walk that we do every year, and we raise a lot of good money on charities, that kind of thing. We're using AI this year actually to help us with some of the marketing outreach, that kind of thing. With no further ado, I'll go through and talk about some of the AI work that we do in relation to the industry, some industry problems. So why IDP? Okay, so IDP stands for Intelligent Document Processing. We've been working in this kind of area for the last 5 years now, if not even maybe a bit longer than that. And we identified quite early on that a lot of time sink in companies is spent scanning documents and then understanding what was in them by humans entering them into 2-3 different systems, and then people making decisions. So we identified that as a great opportunity, and we also noticed that there's lots of inconsistencies in how that's done and how that is prone to human error. So by using AI, actually, we can help kind of improve the consistency of approach. So things are less prone to error and that kind of thing, and then allowing people to focus on the more complex use cases and documents rather than ones that could be kind of processed quite readily. So area and use cases we've kind of used this in. So we use this kind of a lot in insurance. That's why that featured quite heavily. This one's in brokering, so in the Lloyd's market in London. So they do, and the brokers in that syndicate basically underwrite multi-million pounds contracts around insurance. So things like insuring container and vessels for loss, terrorist attacks on buildings, national infrastructure failure, that kind of thing. Normally it's like too big for one insurance entity to cover, so they put it out to broker in the market, and a number of brokers and kind of underwrite that and elements of that industry. However, each time it has to be kind of rekeyed into different brokerage systems before people can and underwriters can make offers on that. So we kind of built this system about 5 years ago. And I'll go through it in a minute, but using a lot of the AWS AI technology at the time, and also some custom models we built. Since then, we've also moved on to pensions and annuities. So this is another kind of use case that we have put to production. Basically, when lots of the work around pensions is done with forms and unstructured data that rise into a mailroom. So if you send in an application form, sometimes it's in the style and format of the insurer, and that's kind of the easy scenario because you're expecting that format, you know where things are. Other times it may be in a broker's format, so it may be that it's a completely different format to what it's still form, but in a completely different layout and style. Things are called differently than what you're expecting. Other times, and because it's like a pension business, and there is times when like kind of lawyers will write letters in around things like to process things in order to grant probate and those kind of things. So you get a mixture from expected format, a mixed format, to completely unstructured text arriving in emails. So we worked with the insurance company, their pensions and annuities team, to work through those 3 scenarios, capture that data, and then present it back and enrich it along the way. And I'll explain a little bit more about how that's done in a moment, but it would go to things like their policy system and loading the policy if the policy number was provided. Another example is customer service. Again, so emails or phones arriving at customer service agent, and with that, and this is in utilities, or we've also done this again in insurance, is just categorizing where to send the email, because a lot of time is spent just understanding which in SME to send it to, or if it can be auto responded. So just indexing and classification of emails is a use case we're focused on. So how we went about it. So conceptually, before we brought it down to individual AWS services, we're looking at these kind of features. So on the left hand side, we have all these different kind of unstructured formats that may arrive, and then what we want to do is process and innovate. So the first phase we looked at is how we would develop the solution. So we used a SageMaker and loaded in and explored the data, and then used either custom models that we built in, or SageMaker models inside SageMaker to develop models and instances of models, or the features alongside of it. When we did it, started it 5 years ago, and it's less today due to now using Bedrock. But back then, we had to actually label documents, so we had to develop in SageMaker Ground Truth the ability to label forms using their UIs, and that allowed us to then have sample documents that we could then fine-tune models on at the time to get the accuracy we needed. I'll come on a little bit more about that in a second. And then as we go through, once you've developed a model, we then had to look at the kind of deployment side of it. So we looked at how to orchestrate it, and that was based on initially, and I'll go through examples, kind of just traditional orchestration, but then we moved to more asynchronous event-driven approach, and more recently into agentic, allowing the agents to decide themselves, or within some constraints, of how to handle individual use cases, and provide some examples of why that's needed. And then beyond that is then the safety and the assurance kind of level. So we had to make sure that we monitor the business KPIs, so the overall performance, things like the model accuracy, those kind of things, and then validate data before it's processed, and then also things like FinOps. So this kind of broadly shows you the stack, and then this shows you the kind of the stages. So what our approach to this solution is we broke it down into these kind of six and a half stages. So sources, those sources that are arriving in. So the first thing we would do is identify that all those sources, so be that a scanned email, image, collection of attachments to an email, etc., would be all classified as one pack of information to process, and that helped to understand the relationship between the documents, and then we'd classify what they are. So for insurance, if it was a policy document or the terms or that kind of thing. So allow us to kind of refine our approach And again, I'll explain that. And then we would actually extract values using some of the AWS services to actually load out things like the policy number, the policy holders details, what they were trying to ensure, those kind of things, and the basic terms, and then complex terms as well. And I'll explain that. Then understanding was like what we soon developed was to know, this is kind of like a top tip, is that we would have to use multiple kinds of models and different approaches, and some of them would be AI or generative AI models, and some of them would just be rule-based statistical models to understand what's in a document and to pull it out and refine some of the understanding what a policy number is, etc., because it may be in a certain format. And then lastly, what we built in as the kind of the sixth layer is kind of the ability to view documents and inform the UI and help it improve. So as we saw more and more documents over time, we could kind of label them and send them back so that the whole system got smarter. And lastly, the kind of the 0.5 layer is the consumption. Depending exactly where it's needed, we'd either push that into an end solution, or we would store it, or we would kind of even provide insights over the top of it. So at least for those like basic cases of indexing, we would understand how well individual agents were performing, that kind of thing. It gives a bit more transparency in the process. So kind of how that translated to an AWS architecture was like this. So to build the pack and to integrate the kind of the source systems, we use Lambda. So that would pull the emails and the attachments, or if it was a scanned image, it would get uploaded to something like S3, and we would pull that all together as a pack, as one kind of one instance of the execution, and that would be saved again into its an appropriate named S3 subfolder, where we could then process it. And then we would use a mixture of techniques. So most of our, and I'll explain a little bit more in detail, but most of it would be then use TextStrat to do some of the classification. But when that was when it was a more bespoke case, we would either use custom models or Comprehends to understand a little bit better. In more recent times, we can also send that now to Bedrock using multi-models to identify what it is. So if it's like I said, if it's a policy document or invoice or whatever it needs to be, so that we could do the appropriate thing. What we found, and this is where kind of the agentic world's changing a little bit due to the understanding, is at that point all these different services from AWS would output different file formats and different styles and different locations, particularly in S3. And we would then have to put a number of lambdas in the middle to kind of bring it all back together to provide a common format to go into kind of the understanding and enrichment layer, where we would then use things like entity classification and those kind of things. What we also worked out, and we've got examples of this later, is where we used things like synonyms. So we noticed quite early on where things would be called different things but mean the same thing, and it would be a way of kind of optimizing the models, and also giving them a bit more information so they don't have to spend so much time focusing on the understanding. The extraction was the most important thing. And then the last kind of implementation layer, like I said, was either we would save it out to something like RDS as a record of truth, or another system. We would also feed it back to ground truth so that it got smarter, and anything that was low confidence got relabeled. Also, kind of what we did was made all of this pipeline configurable at the time using rules, and we have now since updated them. So the rules are more now, if you think about it in the agentic world, it's more like the reasoning, and we kind of that's kind of what that done is like, okay, based on these conditions, these are kind of the reasoning to apply to allow you to drive the rest of the AI. So that's kind of how it's kind of evolved. So that's kind of the high level architecture, and I'll just explain some more kind of detailed bits of it. So the reason why the pack's important is if you look at the ingestion stage, it's kind of some of the pre-processing that you can learn from these things, and the meta. So there'll be things available, like, for example, in the email that would help us inform the list of documents. And we used to say, we save that down to DynamoDB. So like the email address of where it's coming from would be a good example of something we could kind of extract. I mean, and we don't necessarily use the AI for that if we can connect straight into the mail platform. Also, when it was received, when it was processed, helps us to keep building up layers of information, and then we'd update it throughout the process. So capturing the meta would actually help us refine and inform the process. When it comes for classification, kind of this is where some of the complexity of the different services come in, and this is where at the time we still use step functions to handle some of the invocation of different services. But you can see from here, kind of, we would send a PDF. It would give us a number of outputs from text extract, and we'll cover them in a minute. But one of them is the raw text, so all the text in a file. And then we would have to use the step function and a lambda to kind of post and pre-process that into the combined text, which is what in the structure that comprehend required, so that we could classify it. That would output us a zip containing a JSON. Had to get into the JSON to get out what we wanted. So we again had to write a lambda, store that in S3, but also write a lambda to handle it. And then finally, that lambda, just for the classification, like, would update that kind of meta table so that we knew line of business, what kind of thing we were processing, if a policy document, slip, that kind of thing. So to make this a little bit real, I'll explain a little bit what text extract does and why you need to think about these kind of things, and then examples of kind of real world problems we've got to. So kind of text extract kind of gives you these kind of 4 outputs. Analyze documents is pre-trained on 1 million expenses. That's the one we use for this exercise. But you can also do expense where it's been specifically tuned to expense, ID where it's used for ID, and lending for mortgages. And then within text extract, it will basically you've got like 4. You've got the raw text, but you've got 4 sub kind of components you can use. Queries, which will look over all of the document and answer a question for you. Forms, where it will try to kind of lift out forms data, and tables, where it will use text data. And you can see some examples there. This is kind of the output. So the raw output is in just text. The trouble with just text is you lose some of the position of things, where things are located on the page, etc. So that's where we used kind of JSON output. It's very verbose, but it will tell you where every block is on the page, that kind of thing. So some of our logic that we developed allowed you to kind of then understand where something's located. So what we found particularly in a kind of multi-page document, a table would span multiple pages, but only have the headers on one page. So when we got that in text extract, that would be all split up, and we'd have to then put the table basically back together as a logical element. So we had to kind of develop a number of specific logics to help us put that together. Also, what used to garbage it as well would be if there's a footer in between the 2 pages, it used to then treat that as some text in the middle, which was, as humans, we can see as wrong. So it allowed us to kind of put that all back together using X, Y, and boundary boxes to understand that kind of thing. The other kind of challenge, and this is kind of this is an example of some of the challenges you'll face, and this is why meta is important, and understanding maybe who sent you the document, because the date, and I'll use Amazon invoice for this, one of the public images, but you can see it's 0903 here. And now that obviously can mean 2 different things depending on if you're using US date or UK date. And the text extract wasn't clear on that. It knew it was a date and it would extract it, but you couldn't ask it necessarily if it's March or September in this scenario. So we had to develop logic around that. Now, if it's obviously Amazon, we say, okay, it's from their US subsidiary, therefore use the US date. And that's the kind of rule logic we started building up. And also using the metadata to help us know where this was coming from. So if we always thought it was from a certain address from a certain company, we could apply a certain subset of rules to make it more efficient. And then on the query side, you can see here how it struggles a little bit with that what is the 1st of August, because it hasn't got the year against next to it, that kind of thing. So again, we had to write when dealing with either form data, we'd have to develop additional logic to think, okay, it's talking about August the 1st because 2010 is joining it. We had to help again the models with that kind of thing. So that's why, again, formatting data points, updating the table was important. Using another kind of UK example where like context is lost on forms because of compactness. Here is the UK driving license, and a number of the columns are split when you answer a certain question across a number of the pages, and it's TextRack can't understand how they're all related to each other. So we had to build, and you can see it thinks certain things are selected when it's not exclusivity. So we had to put additional logic again to work out, okay, that's a certain layout that infers a certain structure that's not obvious. So in this situation, this is where we use some of the custom we built some custom models. So we used layout LM by Hugging Face and SageMaker to tune it on about 100 to 200 documents or examples, all which would have been insurance forms, etc., to kind of get the accuracy we needed. And so that's one of the complexities in that. So understanding. So you've got all the extraction now, you've identified all your tables, everything that was entered in your form, but you still got to understand what they actually are, what they actually are telling you. So again, let's look at that date period. So what we did do is that, okay, let's see if Comprehend can understand anything more than anything else. And looking at this, okay, it understood that was a date. So by using like a compound of, okay, the compound NER can recognize that it's a date, that was a date, we could apply all around the date. So that's kind of, we could use what we extracted in the frustration with this to understand that we were doing with date and to apply that certain logic to it. However, like Comprehend at the time and still wasn't perfect. Okay, so we look at Amazon simple is from the bill, we look at the next layer down, we look at this and it says, Amazon's organization. Yep, perfect. SimpleDB is a title, okay, and the amount is a quantity, okay, it's monetary, really. And what actually we're trying to do is, if you look at Amazon and SimpleDB there, it's like combined together as humans, we know that's an Amazon service. So it was too kind of generic. So this is what this kind of reflects. So we had to do additional logic to kind of say, okay, combining these things together means a certain thing, and that would actually drive up the accuracy. We've got okay accuracy here, but driving them up. So what you can do in Comprehend, and now also giving like few examples in prompts to LLMs, is give examples of things to fine tune the models. So with Comprehend, we had to retrain the model with basically doing it. So I gave a little bit of data science, even though I'm not a scientist, for a second, but this is basically what it would give you out of the box. And it's all about the final weight of the neural net, basically. And we had to basically give examples and retrain the neural net. So we'd remove that final layer, that last layer, and we train it on samples that we'd labeled in ground truth. And then that allowed us to retrain the models to be, okay, it's a certain layer. So in this uses insurance terms, but that would, for example, you could retrain it to be all the Amazon services, and it would then get a higher accuracy, as we can see here, nearly perfect accuracy for those individual items. and just to go through the last bit of pre-processing, there's still problems that we would come against. So the formatting of these documents, as you can see, is changing. The account number is different. So over here we have account ID and account number, and these are the same invoices from Amazon. Okay, different start at different times, but they've changed their format. So if you're a mailroom with different forms for different providers, or even the same provider, it can change. So this is an example of, okay, what's the account number or the ID? And as humans, we can work that out because we know that they are synonyms, and that's why we developed that synonym logic. But we wanted to make sure that, okay, when we saw the same thing over a number of different examples, that we would recognize them. And likewise, we could build in that January logic to identify the date there where it was, which date format would to apply, and if not. And you can see how it's changed as well. So we had to kind of provide an adapter system to allow it to change. So we built all of those things with synonyms. The other thing we did is for some example documents where we need to, like the policy numbers in a certain format, we didn't even need to use the LLMs or the models to do that work. We could just pick it out using regex. So I think that's the top bit. Sometimes with like FinOps around Gen AI and AI is sometimes simpler is actually better, and optimize some of the usage that way. Again, this is what's total point invoicing versus total amounts due during. Again, this is confusing. So we had to give examples and express rules. Now we in Bedrock we provide examples, and LM's really good at this. But again, it's just the complexity of things being labeled differently and handling them. And then what's the service provider? What's the amount due? Sometimes the column would exist and not exist, and we'd have to infer it, that kind of thing. So we built up the rules. And then lastly, kind of we would put that all back into the database so that we would have that data. And also this is where we also would keep the rules so that we would like if it was a renewal date, a certain logic would apply, those kind of things. So we'd build up that kind of enrichment. And finally is enrichment itself. So the final kind of thing is, if you think about this kind of problem, and this is a problem that we would see, is people spelling their names differently. They're the same person, but people would maybe have a different, how they sign their email signature would be different to how they sign the letter, or how they fill out on the form, that kind of thing. So we would maybe struggle sometimes, like particularly if it's a married couple, because it would be hard to sometimes distinguish between them. So we had to use kind of other systems to look things up. So for example, in a document, we had policy number, and we could actually look up in that policy who was the actual policy holder or who any of the insured parties were, and validate things that we had picked up in that process. So that allowed us to build up that those rules, and over time it was kind of continuous refinement. And what we did, if you're going back to the original kind of AWS architecture, is that whilst it looks like a flow, what we found is that you could feed back in the middle. So enrichment would feed classification, etc. So it may be that we extract a couple of times based on the logic, and once we knew something was better, or use a more refined version once we got to the later stages. So we called the models a couple of times to do that. And that's the same kind of thing you see today in kind of the agentic world, where if it's more goal based, and you call it multiple times. Cool. That's my last slide, as it were. I think Ethan's going to come back on. We're going to open up for any Q&A or any questions.
Cool. Thank you very much for that, Phil. That was great. Has anybody got any questions? We'll just give it a moment. In the meantime, I'll ask one from myself.
Go on.
And it's slightly related, a different question, but what's your favorite AWS service at the moment?
Oh, that's a good question.
What I always like to ask.
And that's got me really thinking. I still like some of the more simpler ones that are not that simple really when you get back to it. But things like S3 I found still mind-blowing how well it performs and what you can do with it. The amount of use cases and data. I always end up somehow back to DynamoDB, S3 and Lambda as like hold fast. It's amazing, even in a fully agentic world.
Yeah, the core classics. Nice. Cool.
Yeah.
Oh, let's see what we've got. We haven't got any questions, but we've had some great feedback in the comments, which is good to see. So thank you for that. Cool. So we're going to move on to our next speaker, Robert. So let me bring Robert onto the stage. Thank you very much, Phil. Thank you. Cool. Hi, Robert. How are you doing?
Hey, hello. I'm doing well. Thank you for having me.
No worries at all. So I will let you move on to your session now.
Perfect.
Cool.
Thank you. Awesome. So today I'll be talking to you a little bit about how you can recharge your GenAI applications with Valkey. My name is Roberto Rojas. I'm originally from Mexico. Usually go by Robert. I'm a senior developer advocate for open source at AWS. And I pretty much talk about day in and out about in-memory databases. So taking a step back about that, right? Like, why do you need an in-memory data store? Mainly because memory is at least 50 times faster than the fastest SSDs, right? That means NVMe SSDs. So when you need to fetch frequently access data, it is predictable. It's a key-based index, so there's no need for seek time. And that's why we say that microseconds are the new milliseconds. So fetching data from RAM or even L2 cache, it's extremely fast. So there are different paradigms or approaches to do this, but the most common one is the cache aside or lazy loading. So whenever you want to go and fetch some data, for example, you have an API, you want to get a product. If you do have that data on a memory store like Valkey, then you simply go and fetch it from location in RAM and you get it within a millisecond. Actually, commonly within 300 or less microseconds. So that's what is called a cache hit. So extremely fast, predictable, linearly scalable. But what happens when you do not have that data? Then in this case, once you fetch data, you present it to the end user. When you do not have the data sitting on RAM, right? So you go and try to fetch it, and then you just try to get it as fast as possible, but you don't yet have it. So that's what is called a cache miss. So that means that you go to a source of truth. In this case, it could be a relational database, just Postgres, where you perform a query that goes and does everything that it has to do, right? Query parsing and then doing the pagination to see where the data is, fetches it from the SSD, and then you get the result, some binary values. What you do then is populate your data onto memory, so frequently accessed, or the next request gets that frequently accessed data. And then finally, you return that product to your end user, right? So very common approach to try to reduce overhead as well as latency and reduce the work that the relational database is doing, or anything, right? This could be an API, or in the case of AI, LLMs as well. So now that we understand data access patterns, we can talk about what Valkey is. It's a key value in memory data store that is mainly used for caching, session, leaderboards, message queues, streaming, and is a like I said, open source under the Linux Foundation. So this essentially happened, or the project was created a couple of years ago from many companies that decided to get together and use the Linux Foundation as the steward of making it that is vendor neutral, and there's no single vendor taking ownership of the project, as well as making as much as possible publicly. So it is fully compatible with Redis open source 7.2.4. That's why Valkey exists. When Redis changed the license a couple of years ago, several companies got together and continued the work that they were doing in Redis open source. So that means it's still built by contributors from the open source community and by industry leaders, such as GCP, AWS, where I work, Alibaba, Tencent, Ericsson, Percona as well has some of the core contributors. And yeah, it's super exciting. There's actually over 60 companies that have worked on the project, and it's available in several as a managed service. How would you be able to use Valkey for GenAI? So with continuous improving multiple features, such as adding vector similarity search back in version 8.1. And like I said, we have a lot of momentum with about 1,500 contributors. I'm sorry, 1,500 commits, 250 contributors, and recently we've passed 145 million downloads on Docker. And the way that you can take advantage of Valkey for your GenAI workloads is by reducing, like I said, the LLM calls. So that means you will reduce latency as well as cost, right? So if you try to use as fewer tokens as possible, then you will be able to have much snappier applications as well as trying to reduce cost, right? So how you do it? I have a demo here that I will show you, and there are 4 different components to this. Actually, 3. We're not using LDAP. This is something from the Valkey bundle that is just a way for you to have multiple of the modules that exist for Valkey in a single container. So the demo is a recommendation system. In this case, you have 2 different personas. I have on the top here a indoor and on the bottom an outdoor fanatic. All right, so that means that they're different personalities, and we will show them different results tailored to their description, right? So in this case, we're looking for headphones, and on the first one, we can see that we get kind of more like gaming kind of stuff, maybe high quality audio. And then on the outdoor, it's more like running or rugged headphones. How do we do this? First, by having the different data types or data structures that Valkey provides. So for example, the hashes is where we keep our products. So they have a brand, a price, a rating, etc. And the thing that is going to allows us to uh, make searches that are relevant is by using the embedding, right? So in this case, I have the last element. It's an embedding of 384 dimensions, and we'll get into a little bit more into what that is. And the user profile, we're using the bulky JSON module for, in this case, because we have like nested elements that we can go and for example, update a single element of the purchase history. I have a couple purchases there with different prices. And then we have preferences as well that has categories, and that's a list on its own. And then the event itself, it's also a list of binary values, right? So the purpose of JSON is the ability to have structure as well as just making a single update that is on a nested element. You can very well use a string for this. You can serialize it, store it as a string, and then whenever you need to read it, you read it, deserialize it, make a little change, and then update, right? The problem with that is, let's say you want to keep the inventory of products like this. So whenever there's a lot of multiple updates into this element, let's say the count of every store, then you're going to have last rider wins, right? So let's say there's people making 2 purchases at once. So there's somebody that decreases by 5, somebody decreases by 10, and then suddenly you should be able to decrease by 15 total, right? But essentially, let's say the 5 wins. So you have a mismatch there. So reduces network overhead, and that's why it's a great use case for JSON data types. The way that you can use it is by performing JSON path queries. So that means that you can also do aggregations or search on in this case, a predicate where we're finding elements from my purchase history that the price is between 100 and 200, right? The next is by using Bloom filters. Bloom filters are a probabilistic data structure that allows us to keep count of the cardinality of elements uh, with a very small memory footprint, right? So about 12 kilobytes of RAM, or depending on the size of the total elements, right? In this case, what it allows you to do is to have precision control. That means that you um, configure your false positive rate. So in this case, when we are creating this vector of bits for tracking which products a user has seen, that's, for example, if you have repurchase on our online retail like Amazon, right? Like it says like, you already seen this product, or produce lacks produce seen, right? So that means that you can guarantee at least that you will never have false negatives. So the main approach here is that you have that security of having no false negatives, as well as up to 98% memory reduction. Let's say you have a list of UIDs, and then you have a million elements, and then you want to keep track of them with precision. Let's say these are users, and you want to see if those users are allowed or not allowed to go into your system, right? So that's how a lot of the uh, firewalls and systems work, right? Where they keep track of IPs, etc., to let users go through it. So this will allow us to keep track of those products that a user has seen. So we have a Bloom filter. In this case, we are reserving the memory, and then having a configurable of 1% error rate, and then 1 items of capacity, 1,000 items. And then we will just mark the product in the second function here, where we have that the user ID has viewed certain products, right? So we will just keep track of that key within and given the product ID. And then we will check if that user has seen the product by providing the user ID and the product ID, and we will check if that element exists within the Bloom filter. And then we will just iterate through all the elements that we want to display. So now, how does the vector similarity search? I mentioned that we have embeddings for both the user, so that means the preferences, the purchase history, as well as on the products. We have a description in the category that it belongs to. So essentially, the vectors are uh, it's a quantity that has direction and value, right? So that means that we can, on a multi-dimensional space, find elements that have certain relevance. So, for example, if you were looking for your favorite song, then we can find other songs that they're very likely, depending on the amount of similars that we find from your favorite one, that is highly probable that you will like, right? That's how a lot of the systems for recommendations work. Let's say you're purchasing, like again, going on an online retail system, so you will get certain ads that will like probably call your attention. Same thing whenever you're going on your streaming service, or you're listening to music on your streaming service as well. They have very good algorithm to try to find that likeness, right? So how does this work? We using the Valkey search module that has vector similarity search, and we just recently launched the full text search as well. In this case, we're creating the vector search by using the products, in this case, using the product colon. So that means we're going to use hashes. So all of the products that have this prefix will be part of the index, where we're going to use the different fields as the brand, search, the region, the price, the rating, and more importantly, that embedding element that I mentioned before, right? So we're going to use the HNSW algorithm, which means uh, hierarchical network small worlds, I believe, something like that. And this is using 10, 24 or over 1,000 dimensions, and we're going to use the metric distance, the cosine, and the cosine is the angle between those two vectors, right? So essentially, that's how we're going to be able to find relevant elements for our, in this case, products, based on the element that we provide, right? So the way that we are going to do it is by using the tags, right? So let's say we want to find like electronics, and then we are also going to provide the user vector, right? So that user is that something that makes it unique for every person or every user in the system. And then we're going to feed that into the search. So we're going to find the nearest neighbors up to 25. And then we're going to iterate through those, ordering by the score. That means the more likely for us to like them. And then we're going to provide a response. So I'm going to move on to the demo here. So I have the two users. I have the indoor person here, and actually there's something interesting that I want to show you. Yeah, we have the network, and then we're going to go here to user 102. Okay, and we're going to search for that headphones that I do know this dataset has. So like I showed you before on the slides, right, that indoor person that has a description of what they purchased before, as well as what they like. We get those more kind of gaming headphones. And if I go to the outdoor person, we do get these like running or rugged headphones, right? So, for example, I do see as well that these googly eyes, right? So that means that I've already seen that product. So what we're doing for GenAI is first providing that similarity, right? So that's how you feed into your LLM, for example, in order to provide the description for this user, relevant results that in this case, we're taking the description of this product and then calling the LLM once. And we're storing this result. As you saw, it was extremely fast, right? So let's say I want to go to product 1388, and this is taking a few more seconds, right? So that means that, let's see, yeah, this is it. So it took, okay, it was actually very fast, 37 milliseconds. Maybe not. I think the HAR, yeah, this one. So this is 1 second, right? I have a local LM, a very small one running on my laptop. But if I go to 1387, now we can see that it's extremely fast, right? So 6 milliseconds. If I go back to the 1388, is 4 milliseconds. That's the API response. So that means that most likely we're responding within less than a millisecond for the database. And if I go back to the headphones search, and then I click on a different one, I see that this actually pre-rendered. That's because what I did is whenever I'm searching, I'm also doing LLM call for the results that I've been given. So that means that, for example, if I click here, I already have a response as well, even though I haven't seen it. And then if I go back and refresh this page, I do see that that product has been seen. If I refresh here as well, I see that both of these have been seen, right? So that's essentially something that you can do now. And now a different demo will be to reduce latency, or I'm sorry, reduce cost, right? In this case, we are performing the LLM call for every product. But what happens if we or somebody already have seen that product, right? And somebody has that has the same kind of characteristics that I do, right? So maybe there's going to be like 3 or 4 different types of persons, like the indoor, the outdoor, the extremely high quality persons, and the low budget as well, right? So they have 4 different personas. So that means that you don't really have to do this for millions of users, right? Like what you can do is define what the different thresholds that you want to have and the different personas, and then that's what you do. So I have a different use case where here we're trying to reduce costs by using something called vector similarity search for semantic cache. So what that does is actually have a little better description here. We have a problem. In this case, we have 3 different queries, right? So this is a database that is it has flights and passengers and things like that. So something that is very common that happens in BI, like people go and ask questions, right? So you have a chat and you want to see like, hey, show me all the passengers on flight 115, and then get all the passenger list for flight 115, and then give me the passenger list for flight list of flight 115, right? So these are different wording, but at the end of the day, it's the same thing, right? So what you need to do is embed these different queries, and then if you have the exact same query, right, like the exact same string, let's say you lowercase everything and you show that it's the exact same, so perfect, right? That goes back to the cache slide that we already saw. But what if it's a different wording? Then you will embed that string and then see if you have a similar query. So what you do is you have an indirect query first to find the cache results. So what you do is you have a list of similar queries, and then you have the result of that query as the value, right? So they do like, oh, I have 5 different ways to say the exact same thing, and these are pointing to this result. So if I have the result, I'd return it. If I don't, then again, you go back to the LLM, right? So that's kind of the use case here. So we have different queries. It's going to generate a query with the LLM. Uh, we don't have it, so it does gives us a result, and then we have a new query again. So it's getting it, is recreating it. But if we do have a hit, right, that means it's going to get returned immediately. So this is the original. Give me the passenger list from flight 115, and then we have one new query that is says, show me all the passengers for flight 115, and as we can see, it's the exact same query as before, right? So the idea here is we're using the LLM to generate SQL queries, but you can do it to do whatever, right? Like generate the description, for example, for the products, or anything in between. And finally, I just want to show you something that we are about to release is the Valkey admin, where you have access to see your clusters. In this case, I have the topology of the cluster, how much RAM is being used, and then I can see the different queries. So for example, remember we were looking at different products. So I have the cache here of those responses that came back from the LLM. We can see the activity as well if we start the monitor, and we can also go and, for example, run different commands here as well, right? So hopefully this was helpful for you, and if there's anything that you'd like to discuss, I'll be happy to help you. Please join the community, go to Valkey.io, join the Slack, and ask any questions. You can go to GitHub as well, and you can start using Valkey just by going to Docker and then doing Docker run Valkey, and that's it. Thank you so much for your time. My name is Roberto Luna, and if you want to follow me on LinkedIn, that's the QR code. Thank you.
Perfect. Thank you very much. That was a great talk. Thank you. Cool. We'll just see, we'll give it a few moments to see if there's any questions. But one question from me, actually, what's been your favorite use case of Valkyrie? Valkey, sorry.
It's probably still gaming. It's kind of my favorite thing. It has different built-in data structures that allow you to create these global scale games, right? For example, sorted sets for the leaderboards, the chatting messaging as well. So you have pops up as well as streams, and with JSON as well. So you can put together all these different data types to create games that are played by 100 million users concurrently.
Wow. Nice. Yeah. Awesome. It's great to think. I mean, some of the services obviously AWS power. It's kind of like, you know, they power so many different big companies at such big a scale. Sometimes you forget just how big. So
yeah, absolutely. Yeah. Something was extremely cool to see is, for example, Amazon Ads runs on Valkey as well now, and they have about 500 million requests per second, right? So it's yeah, wow. Fantastic.
That is insane. Awesome. Cool. I don't think we've got any questions, but please feel free to reach out to Roberto directly via LinkedIn. And please join the Valkey community. They've got an exceptional Slack channel, so make sure to join there. Cool. Well, thank you very much to both of our speakers this evening. We hope to see you all at the next future events. The next AWS AI event will be in London on the 4th of June. And we're being hosted with Arrows. They've hosted us previously before. And it's kind of like a cross meetup with our Azure and GCP communities. We're going to be talking about the difference in AI between all three CSPs. So make sure to join us there. Cool. Well, we hope you all have a lovely evening and we will speak to you soon. That's us signing off.